So let's continue our discussion of Hilbert spaces. To begin with, let's introduce a suitable notion of isomorphism for Hilbert spaces. So we are going to define unitary isomorphisms. So suppose we have two inner product spaces, H1 and H2. Inner product spaces. And suppose we have a linear map. Linear map E. Несколько раз включал-выключал. Спасибо. Okay, so today we continue our discussion of Hilbert spaces. And to begin with, we introduce the notion of a unitary isomorphism between inner product spaces. So if H1 and H2 are inner product spaces, and if we have a linear map from H1 to H2, then we say that U is a unitary isomorphism. A unitary isomorphism. If it is bijective, U is bijective, and preserves the inner product in the sense that the following formula holds for each x and y in H1. Here's a typical example of a unitary isomorphism. Example and a simple calculational exercise. Suppose that H1 is the big L2 space over the circle. So we denote by bold T the unit circle on the complex plane, and the canonical measure on the circle is the usual length measure divided by the length of the circle, so that the measure of T is 1. So H1 is L2 on the circle, and let H2 be the L2 space on the interval from minus pi to pi. And we define U from H1 to H2 by the following formula. So a simple computation shows that U is a unitary isomorphism. Let's now observe that each unitary isomorphism is isometric. This is more or less clear because we can substitute here y equals x, and we see that U preserves the norm. And it's a nice and useful exercise to show that the converse is also true. Namely, each isometric isomorphism is a unitary isomorphism. Or more precisely, if a linear map preserves the norm, if it is isometric, then it preserves the inner product. So our main goal, one of our main goals for the next 2 lectures, will be to give a complete classification of separable Hilbert spaces up to unitary isomorphism. It turns out that this is indeed possible. So, to begin with, we discuss 2 important notions, namely orthogonal projections, and orthogonal complements. We start with the following definition. So we suppose that H is an inner product space. And we say that two elements x and y in H are orthogonal. And we write the following symbol to denote this property. If the inner product of x and y is 0. And we have the following simple result. Actually, this is the Pythagorean theorem. If x and y are orthogonal, then the following identity holds. And of course, the proof is an elementary exercise. Okay, now suppose that we have a subset. Suppose that M is a subset of H, and X is a vector. And we say that X is orthogonal to M, and write the same symbol. If X is orthogonal to each element in M. And the set of all such elements X has a special name. This is the orthogonal complement of M. By definition, the orthogonal complement of M is the set denoted like this, which consists of all vectors, little x and h, which are orthogonal to M. Well, let's now look at some simple properties of orthogonal complements. We have the following proposition. First of all, we observe that the orthogonal complement of any subset of H is a closed vector subspace. It's a closed vector subspace of H. Well, indeed, it's a vector subspace because of the algebraic properties of the inner product. If two elements are orthogonal to M, then their linear combination is also orthogonal to M. And by the continuity of the inner product, this subspace is closed. Second, if you take the closure of the linear span of M and take the orthogonal complement, then this is equal to the orthogonal complement of M. And the reason is basically the same. Is if something is orthogonal to M, then by the algebraic properties of the inner product, this vector will be orthogonal to the linear span, and by continuity, it will be orthogonal to the closure of the linear span. Property 3 is more or less obvious. The orthogonal complement of 0 is H. This is obvious. And the orthogonal complement of H is 0, because if an element is orthogonal to itself, then it is 0 by the axioms of the inner product. Property 4, if M1 is contained in M2, then the orthogonal complement to M2 is contained in the orthogonal complement to M1. This is also obvious from the definition. And finally, what happens if we take the double orthogonal complement? That is, the orthogonal complement of the orthogonal complement. Well, first of all, it's obvious that this set contains M, just by definition, because M is orthogonal to its orthogonal complement. But since the left-hand side is a closed vector subspace, it also contains the closure of the linear span. The closure of the linear span of M. And we will see soon that if H is a Hilbert space, then actually these two sets are the same. But this is not obvious from the very beginning. Okay, let's now introduce orthogonal projections. So we give one more definition. Suppose that H0 is a vector subspace of H. And suppose that little x is an element in H. Then a vector little y in H0 is called an orthogonal projection. Orthogonal projection of x onto H0. If the following condition holds, x minus y is orthogonal to H0. So let's draw a picture. So suppose this is H0. So this is our vector. This is 0. This is our vector x. And this is y. So this vector, x minus y, must be orthogonal to H0. We see that the definition is very natural. It corresponds to our geometric intuition. But our geometric intuition may suggest another definition of an orthogonal projection. Namely, we can define an orthogonal projection to be the nearest point in H0 to x. Fortunately, it turns out that these two definitions are equivalent. So we have the following result, following proposition. I claim that an element y, so this is the first part of our proposition. I claim that an element y in H0 is an orthogonal projection of x onto H0, even only if the distance between y and x and y is exactly the distance between x in and H0. Equivalent, that is, explicitly this means that for each element z in H0, we have the following inequality. So y is the nearest point in H0 to x. And part 2, I claim that if such an element y exists, then it is unique. I don't claim that it always exists, but if it exists, then it is unique. Okay, so let's start with the first part. Let's prove the left to right implication. So suppose that y is an orthogonal projection, and let's show that we have this property. So we take an element little z in H0, and let's calculate the distance between x and z as follows. So for convenience, I take the square and write this in the following form. This is x minus y plus y minus z. Now, this element is orthogonal to H0, so it sits in the orthogonal complement. And this element sits in H0. So these two expressions in brackets are orthogonal to each other. And by the Pythagorean theorem, this is equal to the following. By the Pythagorean theorem. And since this is non-negative, the second summand is non-negative, we have the following inequality. And this shows that we have this, that is, y is indeed the nearest point to x in H0. And moreover, the same calculation shows that this implies that y is a unique element in H0, satisfying this condition. This is a unique nearest point, because if y is different from z, then this is strictly positive, and the inequality is strict. Okay, now let's prove the right to left implication, which is a little bit more interesting. So now we suppose that y is the nearest point to x, and we want to show that y is an orthogonal projection. So let z be an arbitrary element in H0. What we want to do, we want to show that x minus y is orthogonal to z. This will mean that y is an orthogonal projection. So let's apply the following trick. We consider the following function. X minus y plus t z squared. Here t is a real number. So phi is a function of a real variable t, and it is non-negative. And explicitly, we can calculate this function as in the following way. So we have two summands, x minus y and tz. And when we write this explicitly as the inner product, we get the following summands: x minus y squared plus 2t multiplied by the real part of the inner product of x minus y by z, and plus t squared z squared. Well, I skip some details. We have already done such calculation when we proved the Cauchy-Brunikovsky inequality. So we simply write this number as the inner product of this vector by itself, and we get this. So we see that this is a quadratic function of variable t. So its graph looks like something like that. And by assumption, what do we know about this function? We know that y is the nearest point. This means that this function attains its minimum at 0. by assumption, the minimum of phi of t is phi at phi of 0. But it's an elementary property of such quadratic functions that if the minimum is attained at 0, then the coefficient at t vanishes. So the real part of this inner product is 0. Well, this is not exactly what we wanted to show. We wanted to show that the inner product is 0, and we proved only that the real part of this inner product is 0. So to complete the proof, we consider another function. Let's denote it by psi of t, and we define it in the following way. And we apply a similar argument to psi, so we write it explicitly. And we see that a similar argument applied to psi shows that the imaginary part of the inner product, x minus y by z, is 0. Oh, thank you, of course. I t z squared. So we simply insert I here. And when we calculate this explicitly, we will have the imaginary part here. So the imaginary part is also 0. And we conclude that x minus y is orthogonal to z. And this completes the proof, because we observed that we observed that these two conditions are equivalent, and on the way we proved that such an element is unique. So part 2 is also proved. Okay, now a natural question is, how about the existence of orthogonal projections? So we know that it is unique. We know that we have two equivalent definitions of the orthogonal projection. Now, how about the existence? Well, as for the existence, we have first of all we have an obvious necessary condition. We observe that if each element x in H has an orthogonal projection onto H0, then H0 has to be closed. H0 is closed in H. Why is it so? Well, indeed, if this is not the case, if there is an element x in the closure of H0, but which is not in H0, so what can you say about the distance? The distance is 0, of course. So the nearest point in this case is the element x itself. The orthogonal projection, which is equivalent to the nearest point of x onto H0, is x. But this is a contradiction because we assumed that x is not in H0. So a necessary condition is that H0 is closed. And it turns out that if H is a Hilbert space, so far we assumed that H is an inner product space, but we didn't assume the completeness. So it turns out that if H is a Hilbert space, then this condition is also sufficient for the existence of orthogonal projections. So we have the following fundamental result, the orthogonal projection theorem. if H is a Hilbert space, and H0 is a closed vector subspace of H, then each element in H has a unique orthogonal projection onto H0. To prove this result, we need a simple lemma. The so-called Parallelogram Rule. This is a simple identity which holds in any inner product space. H is an inner product space. Then, for each pair of elements x and y, we have the following equality. The proof is an elementary exercise. A little computation shows that this is indeed the case. Why is it so called the parallelogram rule? Well, a geometric meaning is more or less clear. So if we look at the following picture, so this is x and this is y, we can look at the respective parallelogram. So this vector will be x plus y, and this one will be x minus y. And we get the well-known geometric fact that the sum of the lengths of the diagonals of the parallelogram is equal to the sum of the squares of the lengths of all sides. That is x squared plus y squared plus x squared plus y squared. Okay, let's now prove the orthogonal complement theorem. So let x be an element in H, and let little d denote the distance between x and H0. So we want to find an element y in H0 such that the following equality holds. So we want to find the nearest point to x. Then the previous proposition will imply that y is indeed the orthogonal projection. So distance, by using the definition of the distance, this is the infimum of the distances, we can always find a sequence. There is a sequence yn in H0 such that x minus ym converges to D. I claim that Ym is a Cauchy sequence. To prove that this is indeed a Cauchy sequence, we'll use the parallelogram rule in the following way. First of all, we fix a positive epsilon, and we find a natural number n such that the distance between x and yn squared is less than or equal to d squared plus epsilon, whenever little m satisfies this condition. This is possible because we have this convergence. We now take little l, little n, and little m bigger than the same number, and we do the following. So let me draw a picture. We look at the following parallelogram. This x, this will be yn, ym. And this is h0. So we apply the parallelogram rule to this picture. So the sides of this parallelogram are yn minus x and ym minus x. So we have the following identity. And this should be equal to the sum of the lengths of the diagonals. So the first diagonal is just the sum. This is yn plus ym minus 2x squared. And the second diagonal is the difference yn minus ym squared. Okay, now how does it help? So now to prove that yn is a Cauchy sequence, we express this number in terms of this equality. So we conclude that yn minus ym squared can be written as follows. So we have this 2 xn minus y squared plus xm minus y squared minus this, and this we write this number is as follows. We take 2 from here to here, and since we take the square, this should be equal to 4 minus 4 multiplied by, I write this in the following form, x minus yn plus ym divided by 2 squared. I hope this is correct. Yeah, this is correct. Okay, so now what can you say about this? Well, this is, by assumption, this is less than or equal to d squared plus epsilon because of this. This is also less than or equal to d squared plus epsilon. So as a result, we see that this is less than or equal to 2 multiplied by d squared plus epsilon plus d squared plus epsilon minus 4. And what can you say about this? Well, this element, yn plus ym over 2, belongs to the same subspace H0. So the distance between this and this is greater than or equal to the distance between x and h0. So this is greater than or equal to d squared, just by the definition of the distance. And since we have minus here, minus 4 multiplied by this will be less than or equal to minus 4 multiplied by d squared. Okay, we now look at this, and we see that this is nothing but 4 epsilon. Okay, so this holds whenever a little l and a little m satisfy this condition, and this proves our claim. We now see that Yn is a Cauchy sequence. Now we recall that H was assumed to be a Hilbert space, so it is complete, and Yn converges. So Yn converges to some element y, which also sits in H0 because H0 is closed. So we have convergence because H is complete, and the limit will be in H0 because H0 is closed. So this implies in particular that Yn minus x goes to y minus x. But on the other hand, by assumption, this converges to d, and we conclude that the distance between y minus x is d. So our element y our element y is exactly what we are looking for. It satisfies this condition, and so by the previous proposition, it is the orthogonal projection of x onto H0. And this completes the proof. Okay, by the way, a little exercise for you. In fact, we have proved a little bit more, namely essentially the same argument. The same argument shows that for each closed convex subset M of H, and for each x in H, there is a unique nearest point. There is a unique y in M such that the distance between x and y equals the distance between x and M. Formally, we prove this only in the case where M is a closed vector subspace, but actually a similar argument shows that the same is true for each closed convex subset. So the exercise is here. So the existence is the proof of the existence is identically the same, but the proof of the uniqueness is a little bit different in the case of convex sets. But it is rather easy. The projection theorem can be conveniently stated in terms of orthogonal complements. So our next result is the orthogonal complement theorem. If H is a Hilbert space and H0 is a closed vector subspace of H, Then we have the following direct sum decomposition. H equals H0 plus H0 orthogonal. Well, in fact, this result is essentially equivalent to the orthogonal projection theorem, and in particular explains why the orthogonal complement is so called. So why is it a complement? It is a complement in this sense. We have the following direct sum decomposition. Well, indeed, why is it so? First of all, the intersection of H and the orthogonal complement is trivial. This is clear from the axioms of the inner product. Now take any element in H and let little y be the orthogonal projection onto H0. The orthogonal projection of X onto H0. Then we have the following obvious equality, which is trivially true, but the first summoned, namely y, sits in H0, and the second summoned, x minus y, sits in the orthogonal complement by the definition of the projection. So this belongs to the algebraic sum. And since little x was arbitrary, we conclude that we have the direct sum decomposition. And that's it. Okay, and finally, a little but useful corollary of the orthogonal complement theorem. If H is a Hilbert space, and M is an arbitrary subset of H, then the double orthogonal complement to M is equal to the closure of the linear span of M. So we have already observed that the right-hand side is contained in the left-hand side. But in fact, if H is a Hilbert space, then we have an equality here. To prove this equality, we let H0, we denote by H0 the closure of the linear span. So this is called the vector subspace of H. And we already observed that the orthogonal complement of H0 is equal to the orthogonal complement of M. And so the same is true for the double orthogonal complements. And now to complete the proof, now we have to show that H0 double orthogonal equals H0. This is equivalent to our original statement. Well, now to prove this equality, we apply the orthogonal complement theorem twice. First of all, we know that H is equal to the following direct sum. But on the other hand, H0 orthogonal is also a closed vector subspace. So we can apply the orthogonal complement theorem to H0 orthogonal, and we get the following direct sum decomposition. And also we know that H0 is contained in the double orthogonal complement. And these three equalities together imply that we have the following equality. Well, indeed, these two summands are the same, and this one is contained in this one. So if this one would be strictly smaller, then we get a contradiction. So these two summands should be the same. Okay, this completes the proof. Now, our next goal is to discuss orthonormal families in Hilbert spaces. And to prove a classification theorem for separable Hilbert spaces. Okay, let's give the definition of an orthonormal family. Suppose that H is an inner product space, then a family of elements, a family EI, indexed by some set big I, a family in H, is orthogonal if the vectors EI are pairwise orthogonal to each other. EI is orthogonal to EJ whenever I is not equal to J. And if, moreover, the length of each vector EI is 1, then we say that EI is an orthonormal family. Let's abbreviate this as ON. Let's look at some examples of orthonormal families. Example 1. Example 1 is finite dimensional. Suppose that H is Cn with a standard inner product. And let EI denote the following element where we have 1 at the ith position and 0 elsewhere. And then it's immediate that E1 to En is an orthonormal family. Example 2 is similar to example 1, but it is infinite dimensional. Namely, let H now be the little L2 space of square summable sequences. And we define EI in essentially the same way, but now the sequence is infinite. And we get a countable orthonormal family in L2. Example 3 is the famous trigonometric system. Let H be the big L2 space on the interval from minus pi to pi. And the measure on this interval is the usual Lebesgue measure. And we introduce the following functions. We define E0 to be the following constant, 1 over the square root of 2 pi. And for each natural number k greater than or equal to 1, we define ek of t as follows. And fk of t will be the same expression, but we replace the cosine by the sine function. Here k is a natural number. Then there's it is a standard fact, which is very easy to check, that the family containing E0, Ek, and Fk, where k runs over natural numbers, is an orthonormal family. In the big L2 space on the interval. And this is one of the most classical examples of orthonormal families. It naturally appears in many problems, in particular in mathematical physics. And long ago, this family gave birth to the notion of Hilbert space. Okay, example 4. Example 4 is again the trigonometric system, but in a slightly different form. Again, H is the same big L2 space over the interval from minus pi to pi. And for each integer k, we define Ek of t by the following formula. And again, a simple computation shows that the resulting family Ek, where k runs over the integers, in particular it can be negative, this is an orthonormal family, which is also called the trigonometric system. Well, formally it is different from the system from example 3, but it's easy to observe that they are related by simple unitary transformation. Just use the well-known formulas relating the exponent, the sine, and the cosine functions. So this is the reason why this family is also called the trigonometric system. Example 5. And this is again the trigonometric system. But now this will be the trigonometric system on the circle. Namely, now let H be the big L2 space over the circle. As usual, we normalize the measure on the circle in such a way that the measure of the circle is 1. And for each integer k, we define the function Ek by the following simple formula. Then it's easy to show that Ek is an orthonormal family in H. In fact, if we compare examples 4 and 5, And if we recall that there is a natural unitary isomorphism between this space and this space, the isomorphism which was discussed at the very beginning of today's lecture, we see that the functions from this system correspond precisely to the functions from this system. And that is the reason why it is called the trigonometric system. Probably this is the simplest way of writing the trigonometric system. The formula is very simple. And another advantage of writing the trigonometric system in this form is that it consists precisely of unitary characters of the circle. So the circle has the advantage that it is a group under multiplication. And in general, if you have a topological group, then a unitary character is just a continuous homomorphism from this group to the circle. And it can be shown that this family is precisely the family of all unitary characters of the circle. And in fact, it's a general theorem from harmonic analysis that if we take an arbitrary compact abelian group, then the family of all unitary characters is an orthonormal basis in the respective L2 space. Well, I'll define orthonormal basis a bit later, but it is quite useful and important notion. Okay, one more example of an orthonormal family, example 6, is the so-called Rudder system. Rudder system. So to define Rudder functions, it's convenient to draw a picture. So first of all, H will be the L2 space on the interval 0, 1. And to define our functions, we do the following. First of all, we define, we take the interval 0, 1, we divide it into two parts, and we consider the function which is 1 on the first part and minus 1 on the second part. 1 here and minus 1 here. And this will be the function R1. To define the function R2, we divide our interval into 4 equal parts and consider the function which is 1 here, minus 1 here, 1 here, and minus 1 here. And this is the function R2. And so on. So as a next step, we divide our interval into 8 parts and do essentially the same trick. In fact, it's rather easy to write the closed formula. Rn of t is defined to be the sine of the following function. So it's easy to see that Rn, where n runs over the natural numbers, is an orthonormal family in our Hilbert space. And this is the so-called Rudder system. This system has many useful applications in some applied sciences in particular, not only applied but also in probability. And in fact, it is very useful to look at this sequence as a sequence of random variables, independent random variables, taken values +1 and -1 with probability 1/2. Okay. Well, since we are mostly interested in separable Hilbert spaces, let's observe the following simple result, the following proposition. If H is a separable inner product space, then each orthonormal family in H is at most countable. The proof is based on the well-known Dirichlet principle. You have uncountably many boxes and countably many rabbits sitting in the boxes. Then there is always a box with no rabbit inside. So formally we do the following. We suppose that EI is an orthonormal family in H. And we observe that the distance between EI and EJ is precisely the square root of 2 by the Pythagorean theorem. So this implies that if we take any real number r, which is less than or equal to square root over 2, and if we take the open balls of radius r and centered at EI and EJ respectively, then the intersection of these balls is empty, just by the triangle inequality. Okay, now we take, so H is separable, so we can always find a countable dense subset. So let Xn, where n runs over natural numbers, be a countable dense subset of H. Well, since it is dense, it has a non-empty intersection with each non-empty open set, and in particular with each ball of this form. So for each I, we can always find a natural number n of I such that x n of I belongs to this ball. But since the balls are disjoint, we conclude that the map from I to n, to the natural numbers, which takes each little I to the respective natural number n of I, is injective. Just because the balls are disjoint. But this can happen only if I is at most countable. Okay, let's now prove some general properties of orthonormal families. One of the most important properties is the following result. A very important but a very easy result. Suppose that we have a finite orthonormal family. So H is an inner product space, and U1 to En is a finite orthonormal family in H. And let H0 denote the linear span of this family. So we take an element x in H and let Ck denote the inner product of x and Ek, where k runs from 1 to n. Then, first of all, I claim that the following element y, given as the following finite sum, is the orthogonal projection of x onto H0. And second, we have the following formula. The distance between x and H0 squared is given by the following formula. This is the norm of x squared minus the following sum. The proof is elementary. To prove that this element is the orthogonal projection of x onto H0, we have to show that x minus y is orthogonal to H0. But since H0 is spanned by E1 to n, it's enough to show that x minus y is orthogonal to each element Ej. Well, but what is this? This is the inner product of x and Ej, which is Cj minus sum from 1 to n, Ck, Ek, Ej. But since the family is orthonormal, only one summand survives, namely the summand where k equals j, and the respective inner product will be 1. So we see that this is Cj minus Cj, that is 0. And that's it. So this shows that y is the orthogonal projection. And part 2 readily follows from part 1 and from the Pythagorean theorem. Namely, by the Pythagorean theorem, we have the following inequality. Now the norm of y squared, so this is y. When we calculate the norm of y squared explicitly, again by using the Pythagorean theorem, we see that this is the following sum, again by the Pythagorean theorem. And by the definition of the orthogonal projection, not by the definition, but by one of the main properties of the orthogonal projection, namely y is the nearest point to x. We see that this is nothing but this norm is nothing but the distance between x and H0. And that's it. So we get a formula which is equivalent to this one. The numbers Ck, which appear in this proposition, have a special name. They are called the Fourier coefficients of x with respect to our orthonormal family. And of course, this definition makes sense for all orthonormal families, not necessarily finite. So we give the following definitions. The following definition. If, well, suppose that we have an orthonormal family, EI, in H. And let little x be an element of H. We define the ith Fourier coefficient of x with respect to this family to be the inner product of X and EI. Our previous result states probably the main geometric property of Fourier coefficients. So, as I said before, we will be mostly interested in separable Hilbert spaces. So from now on, we assume that EI is an at most countable, and we abbreviate this as follows. AMC will mean at most countable. Orthonormal family in H. And since it is at most countable, we may assume that the index set I is either the set of natural numbers or the finite set of natural numbers from 1 to n. Okay, now we have the following corollary from the previous proposition, which is called Bessel's inequality. So I claim that for each x in H, the following inequality holds. Where Ci is the ith Fourier coefficient. So in particular, we see that if our family is strictly countable, that is the set of natural numbers, then this series converges. If I is the set of natural numbers, then the series squares of Fourier coefficients converges. So this is Bessel's inequality. And this corollary is immediate from the second part of our proposition. So what we do, we just fix an arbitrary n. We look at this formula. And since this formula is true, we see that this number is non-negative. So this number is also non-negative. So all finite sums of ck squares from 1 to n are dominated by the norm of x squared. So if I is finite, then this completes the proof. And if I is the set of natural numbers, we just take the limit over n, and we get this. So Bessel's inequality is mediated from this equality. Okay, so that's all for today. And at the next lecture, we prove some more results on orthonormal families. We will show that each separable inner product space has a sufficiently large orthonormal family, the so-called orthonormal basis, which is by the way not a basis in the algebraic sense of the word. It is a kind of a topological basis. And eventually we will see that each infinite dimensional separable Hilbert space is unitarily isomorphic to the little L2 space. Okay, thank you.